Okay, for our second speaker, okay, on the topic of haptics, I'll just hand over straight away to the speaker. Okay, let's begin.
Okay. Hi, I'm Ceenu George. I'm from LMU Munich in Germany. And this work was done in collaboration with Mohamed Khamis, who is the main author on this project, and he's also dialed in and available for the questions afterwards. And he was in Munich before, but he's now at the University of Glasgow. So today I'll be talking about our project ElectroCutscenes. It's playing up. Okay. So although there are many applications for VR, VR games are one of the biggest markets for VR. The revenues of VR gaming sales are projected to reach up to almost $23 billion in 2020. In this work, we improved the immersion in cutscenes in VR games. So let's go into what cutscenes exactly are. Basically, cutscenes are pre-recorded scenes that are run during gameplay. In those cutscenes, the user is passive and not interacting. Instead, the player is only perceiving the scenes using visual, audio, and haptic feedback. Cutscenes are a major component of any game. Oops. You're probably... Sorry. He's saying something in the background. So my Skype is coming up, sorry. So cutscenes are a major component of any game. Sometimes they are referred to as in-game cinematics or in-game movies. Cutscenes are usually there to tell a story, for example, explaining an event at the outset of the game or showing a conversation between game characters. Sometimes they are used to explain to players how to control the game or how to use certain items. Cutscenes in their current forms are limited in many ways. As I said earlier, cutscenes are passive scenes where the player is not interacting. This means they are less likely to be immersed. Cutscenes are usually short and can benefit from a focused, immersive experience. There is a lack of work on using feedback modalities other than tactile, visual, and audio in cutscenes. So in this work, we propose ElectroCutscenes, a concept for delivering cutscenes in VR that are highly immersive, realistic, and elicit high subjective presence. We do that by exploiting electric muscle stimulation, in short EMS, to actuate parts of the body to match events taking place in the cutscenes. This results in the user performing movements involuntarily, which in turn makes them feel more present in the game and makes them enjoy the games further. I'd like to show you now a video that explains how it works. So, here you can see a user wearing a HTC Vive headset. We've placed electrodes on the user's arms in specific places to elicit the movements that match the scene. I will explain in a bit how we choose the positions of the electrodes. Sorry, the video should have played. My screen has frozen. Give it a second. No? Okay, no video then. Okay, so we use electric muscle stimulation to elicit the movements. By placing two electrodes on the user's muscle and passing an electric signal, we cause the muscle to contract involuntarily. Sorry, my screen is frozen. I'll have to reset the presentation. Let's try this again. It was working before in the test run. Okay, so there it is. So as I said, we use electric muscle stimulation. Basically, we place 2 electrodes on the user's muscle, and then we pass an electric signal that causes the muscle to contract, which is what you can see here. This results in the user moving their arm unintentionally. So the setup consisted of 4 main components: an EMS generator, EMS control module, a desktop PC, and a VR headset. The first 2 components are based on the open source toolkit by Pfeiffer, who is also a co-author, called Let Your Body Move. We use the Stim Pro X9 Plus for generating the current. The exact configuration and details can be found in the paper. The device was connected to 2 Arduino control modules, each powered using a 9-volt battery and connected to 2 pairs of electrodes. This means that in total we could use up to 4 electrodes. I won't go into the details because of time now, but you can find the details of the implementation in the paper. So, the way it worked is that the cutscenes are generated on a desktop PC that runs Unity. The PC communicates the cutscenes to the VR headset. In our case, as we saw earlier, this was an HTC Vive. The headset renders the scene. At the same time, the PC also sends instructions to a control module. In our case, we used a smartphone that runs an Android app. The app receives instructions as to which muscle should be actuated and when. These instructions are then received by the EMS toolkit which actuates the movements. So you might be wondering now why we use the Android app. In practice, we can directly connect the PC that generates the cutscenes directly to the toolkit. But in our prototype, we prefer to have a separate device that the experimenter can carry during our user studies and allow her to intervene if needed by, for example, actuations of a specific scene or aborting them in a case of an emergency. However, for our study, we didn't end up using this feature. So now into the evaluation. The aim of the experiment was to understand the effectiveness of ElectroCutscenes in improving presence and realism in VR cutscenes. We invited 22 participants aged between 19 and 30 years, and we compared ElectroCutscenes to 2 baseline conditions under 3 cutscenes. Our study followed a within-subject design where all participants went through 3 conditions of 1 independent variable, ElectroCutscenes, and 2 baseline conditions, vibration and no feedback. We experimented with 3 scenes that resemble common cutscenes in today's games. Okay, so the videos are playing. Our experiment involved 3 conditions. In the EMS condition, we used electric muscle stimulation to actuate the movements to match the scenes. In the vibration conditions, the participants held the controller from the HTC Vive, and the respective one vibrated at the appropriate times in the scene. This was a baseline condition, as most VR headsets come with handheld controllers that vibrate to provide tactile feedback. In the no haptic feedback condition, the participant only perceived the scene visually and through audio. You can see here they were wearing headphones. Okay, so I'm not going to play this just in case my screen freezes again. So as for the cutscenes, we use 3 sample cutscenes. In the first cutscene, a burning car approaches the user and then explodes. In the second cutscene, an avatar approaches the user, shake their hand. Okay. And in the third cutscene, a bird asks the user if they have a key to their cage. The user then raises their hand and opens it to find the key glowing in their hand. Although the scene seems very interactive, but the participants were told not to move or interact in the scene. Instead, they only had to passively perceive the feedback. So for the explosion scene, we actuated the lateral part of the deltoid muscles on both arms to raise them sideways. This resulted in the effect you see on the bottom right. As for the handshake scene, we had to perform 2 consecutive actuations. First, we had to raise the forearm by actuating the biceps. Second, to simulate a handshake gesture, we actuated the flexor digitorum muscle, which lies on the anterior part of the forearm. This was done to flex all fingers except for the thumb. Then simultaneously we actuated the extensor digitorum to extend the same 4 fingers. Doing both actuations together caused a grasp gesture, which we saw earlier in the video. So for the handshake scene, we had to perform 2 consecutive actuations. First, we had to raise the forearm by actuating the biceps. Second, to simulate a handshake gesture, we actuated the flexor muscle, which lies on the anterior part of the forearm. The details of the muscles can also be found in the paper. This was done to flex all fingers except for the thumb. For the hands opening scene, we again actuated the biceps, followed by the extensor, to extend the 4 fingers. Note that this does not rotate the hands to the palm face, so that the palm faces upwards, as seen in the image on the right. This allowed us to discover a very interesting phenomena, which we will explain in a few minutes. So the end result looked like this. Note here, although we did not rotate the user's hand so that the palm faces upwards, as you can see in the figure, the participants rotated their hand so that their posture would match that of the virtual avatar. This is one of the most important findings of this paper. In 12 out of 22 cases, the participants who perceived EMS feedback complemented the EMS actuations due to the visual feedback. This was observed only in the EMS condition and not in the other conditions. The reason this finding is very important is that it means that it might not be necessary to actuate each and every muscle of the human body for a realistic kinesthetic feedback. Instead, we can actuate parts of the movements by actuating superficial muscles that are straightforward to reach using EMS, and then use visual feedback to nudge users to complete the movements. So the evaluation. Participants put on the HTC Vive headset. We attached the electrodes and connected them only in the EMS condition. Participants underwent a calibration session. In the calibration session, we followed procedures from previous work, which used EMS in HCI applications. We gradually increased the intensity until the movements were acceptable. We ensured that the stimulation was comfortable and not painful, and no participants reported any pain during the study. The intensity was also set to be weak enough to allow the user to override the signal if needed. Calibration took 10 to 15 minutes per participant. The EMS generator and control modules were placed in the backpack that the participants had to put on. Participants went through 3 blocks, 1 per condition. In each block, participants watched all 3 cutscenes. The order of the blocks and scenes was counterbalanced using a Latin square. Afterwards, participants filled 2 questionnaires and were interviewed at the end of the study. The limitations. So the limitations of our study: in the vibration condition, participants had to hold the controllers. In the other conditions, participants did not have to hold anything. So this might have had an impact on the results. We use controllers because these are the standard haptic feedback devices in commercial systems. Another issue is that the electrode placement and calibration took quite some time, about 10 to 50 minutes for the setup of the electrodes and to calibrate. However, this problem is expected to be addressed in the future with the development of haptic technologies such as the Tesla suit and other examples which we provide in the paper. So now to the results. We asked participants through a questionnaire how realistic the scenes were and how consistent the feedback was with the scenes. Realism was statistically significantly higher for EMS compared to the no feedback condition, and consistency was significantly higher for EMS compared to the other two conditions. We asked participants to fill in the IPQ questionnaire. The mean IPQ scores show that the EMS results in higher spatial presence, sense of being there, and involvement. Those improvements were statistically significant, according to ANOVA. The mean perceived realism was slightly higher in case of EMS, but the improvement wasn't statistically significant. In our observation, we noticed that some participants performed movements that we did not actuate using EMS. They performed them only in the EMS condition and not in the other conditions. In particular, in the scenes showed at the bottom, we did not rotate the participants' hands to face upwards. We only raised their forearms and extended their fingers. So let's take a look why they actually move their arms upwards. In our observation, we noticed that some participants performed movements that we did not actuate. They performed them only in the EMS condition and not in the other conditions. In particular, in the scenes shown at the bottom, we did not rotate the participants' hands to face upwards. So, complementing EMS actuations. Participants respond to visual feedback differently in the EMS condition. Can partial EMS actuations nudge users to complete the entire movements? This is very helpful for future EMS applications where the muscles are too small to actuate or deep inside the user's body so that actuating them would cause pain. So there are two main take-home messages from this talk. Using EMS for kinesthetic feedback improves perceived presence and involvement in cutscenes of VR games. Partial EMS actuations can be implemented by users if the right visual feedback is provided. So Mo is also looking for students who can support him doing this work. And that's it. Thank you very much.
Time for questions.
Well, thank you for your presentation. I wanted to ask, do you know if there is any medical impact for the user if he has electrodes for a long-term use?
Can you just give me a second? I'm dialing in Mo as well.
Okay.
Yes, I'm here. I'm not sure if they can hear me already.
Yeah, they can hear you.
Okay, perfect. So yeah, I think I heard the question. So the question was whether there are any medical or health implications of using EMS for a long time, right?
Yes.
Yes. So I'm not aware of studies that investigate that. I mean, definitely there is, especially in the medicine domain. EMS is also used for exercise, so for like in gyms, for example. So of course, applying EMS in the wrong way or in like, at very high intensities would cause muscle fatigue. And also, there are some certain parts of the body where you shouldn't put electrodes. So yeah, care must be taken when using EMS. Yeah, that's what I can say about EMS.
Okay, thank you. And I have another question. Did you try to put some vibration on the arm to compare with the EMS on the arm too?
We haven't done that. So actually, we discussed this in the paper because, one big difference, and also as we showed in the limitations slide, is that we had people hold the controllers in their hands, which vibrated, and this is slightly different than putting the vibration motors on the arms. So we haven't done that, no. I think it would have been unfair for the vibration condition if we had done that, because with EMS we use we elicit kinesthetic feedback, and this results in the arm moving. But basically, if you have seen the explosion scene, if we had applied vibration on the biceps, it doesn't correspond to what the person sees in VR. So it's not always possible to use vibration to do something similar to EMS. That's a problem.
Okay, thank you.
Thank you. My question is a bit about agency. I'm curious to, this idea of your muscles forcing you to shake someone's hand without being motivated to do it, perhaps. Or how did any of the participants talk about that side of things in terms of, because it wasn't something that it was the muscles that kind of made it work, and I'm kind of interested in that in terms of those partial. There seems to be a lot of positive about the partial EMS actuations, because they kind of set off some decision making in the participants themselves.
I'm sorry, I couldn't.
The question was about agency.
Yeah.
Agency.
So, I mean, I understand that the muscle activations, vibrate the hand, and therefore, in one case, it's about shaking someone's hand. Now, the muscle, that's not a thought that someone has come up with. It's the participants are being nudged to do that. So my question is, did the participants talk about that at all? And also, I can see the potential in the partial nudge EMS activations as kind of interesting, because they sort of set up a train of thought in the participants themselves. Does that make sense?
Yeah, so sorry, the sound is not very clear. Sorry if I interrupted you, but so basically, yes. So basically, so we had, as Ceenu explained, we had three conditions. There was the EMS condition, and there was the vibration one, and the one where they didn't have any type of feedback. So they only performed these what we called complement, the cases where they complemented the EMS feedback. This only happened obviously in the EMS condition. So for example, the people who rotated their hands upwards in the third scene, they did that only in the EMS condition and not in the no feedback condition. So I think that there is an interesting interplay here that obviously this has to be explored more in future work, and I think there's a lot that could be done in this area to see how much of visual feedback do you need to provide to the user to set the context and to nudge them to complete the movements, or complement the EMS actuations. Because I mean, for us that was kind of a very interesting observation, but it wasn't the main aim of our study, and it was kind of a side observation. I think that this must be explored in future work in more depth. Because I think, there are things that are very hard. There are muscles that are very hard to actuate, either because they are too small or they're too deep in the body. And I think if we can leverage this opportunity of combining visual feedback and EMS, we could let people perform movements that EMS alone wouldn't be able to actuate or elicit. Does this answer your question? I'm sorry if I misheard some parts.
Yes, thank you. Yeah, just go ahead.
Oh, thank you. Have you tried or think about trying in the future of controlling the condition with incongruent movement? Let's say applying the EMS in a congruent fashion versus incongruent fashion. In that way, you can sort of control the other sort of psychological factors like the decision making or whatever. So the compatibility between the EMS
so
induced movement,
congruent, like the movement
the scene,
wouldn't be
yeah.
aligned, or
No, the congruent with the movement in the scene.
so it wouldn't be aligned with what they're seeing in the scene.
That's right. So have you considered doing that as a control?
We haven't looked into that. No. I think it would be interesting to see. I mean, in particular related to the phenomena I was just talking about now, where people complement the movements. It would be interesting to see if we actually need to do just move the muscle in a way, or if we like to what extent. So if we take the handshake example, do we just need to raise the hand like that, or do we actually need to elicit the grip move in addition, or maybe only raising the arm is sufficient. So I think that will be interesting to look into, to see, also to explore this phenomena further.
Kia ora. This is an absolutely fascinating topic, and it's good to see that you've put some thought into giving the user the ability to, override the stimulation if it's something they're uncomfortable with. But I was wondering, what kind of margin of error is there for a comfortable calibration? Like, could you perhaps speculate as to how likely it is that something could go wrong and it could result in discomfort? What kind of margins are we working with here?
So what we did is that we had a calibration session which took a lot of time for each person, and we continuously asked the participants how they feel about it, if it's comfortable or if it's starting to hurt. So I think, the way I would do it is by having this feedback loop, or getting input from the participants on whether they feel okay still, or if it hurts. And of course, there should be mechanisms to abort the whole thing, either whether it's in experiments or in real use. So, for example, in the study, the experimenter had a phone with an abort button, just in case anything goes wrong. She would then press the abort button just to stop everything. And I think we should have such mechanisms in place.
Quick follow-up, do you have any speculation as to how you might incorporate that abort button for the user, so that in an environment where they're alone, in a commercial application perhaps, they could have that functionality? Any current thoughts on how that might be done?
Mm-hmm. So I think ideally we wouldn't be in that stage that we have a commercial product where where something could go wrong. So at the moment there's also work on using having sleeves of where you have several electrodes and also EMG to kind of calibrate automatically. And I think there's a lot of advances also on the hardware side there. So I think ideally we would reach the stage where things are calibrated at an ideal, level where people are you wouldn't need something like that. But if it's, if there is a need to or I mean, just as a backup option, I think having a button or like something like, for example, in case of using HMDs or VR, I mean, you could have a button on the head-mounted display that you can press, because people could always override the signal, like the actuation. So even if my arm is being moved somewhere else, I could just override it and press this button to, stop the EMS.
Just to follow up on that idea, can the system be hacked? Just wondering if somebody from outside could take control of somebody else through VR.
So I haven't looked into that, although it's actually very interesting, because I'm now doing a lot of work in usable security and human-centered security. Of course, that's a threat that we should account for. So it would be really bad if somebody hacks into someone's HMD or EMS and actuates certain movements or forces the user to go open the door for them or something. We haven't looked into that, but I think it's a very important topic, and it's I mean, not just for the EMS, but also for the entire VR experience. I mean, imagine if if you hack into someone's HMD, you could really hurt them. So I think this is very important as well. So to answer your question, I wouldn't be surprised if somebody is able to do that now or in the future, and this should be something that we should account for.
Right. Okay, well, thank you very, very much, and I'd appreciate in connecting from Glasgow.
Yep.
Okay.
Yes.
Okay. Thank you very much. Okay, everyone.
Yes,
Round of applause. Thank you very much.